Previously on classical mechanics, there's a thing called the action, which is the integral of Lagrangian, which is minimized. That means that the coordinates must obey the Euler-Lagrange equations, which are these. This quantity here is called the conjugate momentum of Q. With the momenta, you can construct the Hamiltonian, and the Hamiltonian is an alternative way of writing your equations of motion in classical mechanics. If you have a symmetry of your problem, where you make a continuous family of transformations that do not change your Lagrangian, then you have a conserved quantity. Now, we introduced Noether's theorem last time, but let's do a couple of examples so we're sure how that works. Now, the absolute simplest system, which we've got a very clear symmetry of the Lagrangian, is just a free particle. In one dimension, the Lagrangian is just the kinetic energy, which is a half m times the velocity squared in the non-relativistic limit. And we can see that if we take that whole system and we move it over, then we get exactly the same. And so if we do a translation on our coordinates, so we're relating our old and new coordinates just by adding an s, then in fact, if we do the mathematics, we can see very trivially that the Lagrangian is the same. We just replace the old coordinate with a new coordinate. We have exactly the same Lagrangian. That means, from Noether's theorem, is that we have a conserved quantity. And that conserved quantity, which doesn't have a sum because there's only one coordinate involved, is calculated like this. So we've discovered the conservation of momentum. And that's a fundamental statement of the universe, that the conservation of momentum comes from the translation invariance of the Lagrangian. Let's try another example. Let's try a rotation. Now, in a rotation, we need at least two coordinates. Let's have an x and a y. Suppose our x and a y were rotated and will be cos theta, sine theta, minus sine theta, and cos theta. So that's a normal rotation matrix. And so our old coordinates and our new coordinates are related by rotation. And suppose we still have this free particle. Then beforehand, my Lagrangian was a half m x dot squared plus y dot squared. And if we calculate the new one, we find that that's the same. So we have a conserved quantity. And that conserved quantity is given to us by Noether's theorem. This time our variable is theta rather than s. And this time we have two terms in our conserved quantity because we have two variables. And we can expand that out. And if we examine that for a moment, we might recognize that as, in fact, the z component of the angular momentum. And so Noether's theorem has given us a second principle, which is that symmetry with respect to rotations gives us conservation of angular momentum.